All right, you're good.
Alrighty, I'll be starting everything off. Hello, Philip. My name is Jeremy Kreis. I am a mechanical engineer.
My name is Joe Carpenter. I'm also a mechanical engineer.
I'm Kat Altman. I'm also a mechanical engineer.
I'm Riley Clark. I'm an industrial engineer.
And I'm Connor Popo, and I am a material science and engineer.
And we are the flowserve capstone team. Throughout this semester, we have searched to find a new way to verify measurements of the inlet and outlet of various cast impellers given to us by flowserve. Riley is now going to go on to tell us a little bit about the problem that we were presented with at the start of this semester.
So first, to begin addressing this issue, we had to first understand what steps had to be taken and where they fall short, along with understanding potential solutions on the market. So the problem statement here is currently tools being used by flowserve are inconsistent, inaccurate, and not standardized. The inlet geometry of the impellers that flowserve provides is difficult to access, which means current tools on the market aren't built to measure them accurately and efficiently. So some tools may work for outlet geometries and some may work for inlet geometries, but not both. There isn't a current solution for both. So we're tasked with creating a tool that can do both. In addition, different branches are using different methods to verify the geometries of cast impellers. There isn't a standardized method across all branches. One example is a device you can see in figure 2. It's a 3D printed go no-go gauge, which accesses the inlets and outlets of impellers, but this is also not a universal one-size-fits-all tool. So this tool helps determine the width, if it's accurate or not. And this tool doesn't fit, like I said before, the catalog of flowserves impellers across the entire catalog. So in addition to this tool isn't the most accurate method, so we are tasked with creating a better, more accurate, and more efficient way of doing this. Now I'll pass it to Joe to discuss the problem to find a solution.
As you can see above, we've broken down the approach into 5 main categories. The first category was research. This was a crucial step because in order to move on to the next step, we need to determine some of the issues with the current measuring devices and practices. This allowed us to have a better understanding of exactly what we needed to improve, the purpose of these improvements, what the purpose of these improvements would serve. The next step was understanding the problem. This is where we used the research in the previous step to help determine the specific points on the impeller that our device is used to measure. Next was the brainstorming phase of possible solutions. This entailed multiple meetings, both within the team with our advisor, Dr. Letty Het, who specializes in metrology, and our flowserve sponsor, Philip Garcia. Once we agreed on the best, most workable idea, we moved on to the prototyping stage to develop a working device. The prototyping phase lasted the longest because we had to prototype, test, obtain feedback from ourselves, Philip, Dr. Letty Het, and then reshape the tool to test again. The prototyping process mainly used CAD models and 3D printing to accurately assess our ideas. Once we were comfortable with the final design, after many iterations of prototyping, we then moved to manufacturing our tool out of 1/8 inch 180 steel with a plasma CNC cutter. From there, we grinded down the feet on each end of the tool to calibrate it so that both the inside and the outside measurements were accurate to the point of plus or minus 0.1 millimeter. Overall, this process led us to a successful outcome, which Kat will tell you more about on the next slide.
So our final product is shown in figure 3, both in the open position and the closed locked position. And our CAD drawing is in figure 4. And as you can see by the red arrows, our design is integrated into a pair of snap ring pliers that are cheap and can be found at Lowe's, Home Depot, stores like that. So integration is really easy and there's minimal manufacturing. The design is also mirrored, so whatever the measurement is on the inside of the impeller at the top of the tool is also mirrored at the bottom of the attachment. Then from here, calipers can be used on the bottom of the tool to obtain the distance between the feet, and then that is the measurement on the inside of the impeller. Then there were also feet added, so that way the measurements are inside measurements and only one part of the tool touches the inside of the impeller at a time. This way we could get more accurate measurements. And the snap ring plier also has a spring in the tool. So this way it's in a naturally open position. So that way the same pressure is applied to the tool whenever measurements are being taken. And this avoids the issue of different people applying different pressures and possibly messing up the measurements. And lastly, there's a locking mechanism with wing nuts that allows the user to hold the position that the tool's in for ease of measuring. So what you can do is once you get the tool in, you find your measurement and then you just twist it to lock it. And from there, you don't have to worry about losing that measurement while you grab the calipers to measure the bottom mirrored feet to get the distance. So now Jeremy's going to discuss how well our final tool met the original criteria that we were given at the start of the semester.
One of the most important criteria that the team had to meet for this measurement tool was improving upon the accuracy of flowserve's current go, no go gauge. Coming into this project, we were informed that flowserve wanted to ensure that a measuring tool could obtain an accuracy of at least plus or minus 0.762 millimeters from the exact dimension. With a mirrored X scissor-like design that Kat just mentioned, the user is now able to obtain an inlet and outlet internal dimension without having to extract the tool to obtain that measurement. This allowed for a more accurate measurement and reduction in potential user error that could arise in withdrawing the tool. Through tedious manufacturing and machining, the team was able to calibrate each side of the tool within plus or minus 0.1 millimeters, so our tool met this requirement. Although calipers still need to be used, making this measurement procedure a two-step process, the ability to access impeller inlet and outlet locations adds significant confidence that flowserve parts are meeting required specifications. This measurement process can be seen in figures 5 and 6 below, where we can now see both of our tool and calipers being used together. Another requirement that needed to be addressed was the ability for our tool to access the unique geometries present in the impellers and to ensure that it could be used over a range of impellers that we were given from flowserve. For additional measurement accuracy, the team implemented a locking mechanism, as Kat had mentioned, that can be locked when obtaining a measurement. With this locking mechanism, it would be difficult for one person, without this locking mechanism, it would be difficult for one person to obtain a measurement on their own. Additionally, due to the bend that we implemented, the 25 degree angle bend, we can easily access that inlet and outlet geometries while avoiding the impeller hubs. Both of these requirements were satisfied and implemented into our final design. Overall, the team was able to create a tool that could work efficiently and meet all requirements that were given to us at the beginning of this semester by flowserve. But with any design, there is still the ability to improve upon it, and those improvements will now be touched on a little bit by Connor as we wrap up today's presentation.
Yeah, so overall, within the last 15 weeks, our team has managed to take the quality inspection issue that flowserve presented to us and research, prototype, test, and finally manufacture a tool that met the needs of the company. If we're going to give more time, we feel we could optimize the tool even more, which may be something that flowserve looks into in the future. However, considering our tool already meets the requirements, these optimizations and improvements may prove to be unnecessary. These improvements could potentially occur in two areas. If you look at figure 7, the circled section areas, the locking mechanism can become more ergonomical. The current screws used stick out, which may be an annoyance to the user. The second being potentially adding another bend in a different plane to step the tool away from the hubs even more. However, this creates a curvature issue, which when the tool opens, curvature area issue when the tool opens. So much more research would need to be done by flowserve if this is of interest. Additionally, for manufacturing process, we may advise water jet CNC cutting over plasma CNC cutting. Since we're working with very thin material, as you can see in figure 8, there was a lot of heat generated in plasma cutting, which can easily lead to issues from our thin metal. As of now, if flowserve were to mass manufacture our snap ring plier attachment and equip all their quality testing sites with our tool and a digital caliper along with our inspection manual, we feel that flowserve will be able to get more consistent and accurate quality assessments of their impellers. This concludes our presentation, and we open the floor to any questions.
Thanks, everyone. That was a pretty good presentation. So yeah, I do have a couple questions. One of them I think I kind of asked you last time, but I just want your guys' final say on it. So after everything's said and done and you have the final design prototype built, how much easier in terms of like ergonomics, not necessarily accuracy, do you feel like it was to take measurements with the tool you created in addition to the calipers versus just the calipers by itself? Again, I haven't played with it myself, so I can't say anything. But yeah, how difficult was it to get it in place? Use, I guess, another hand to tighten the wing nuts, and then I guess use that same hand to go and grab calipers and take that measurement on the exposed end. Was it as easy as you thought it was going to be? Maybe a little more difficult, or probably just as difficult as it is just using a pair of calipers by itself?
Go ahead, Jeremy.
This related a little bit to my slides, so I figured I would give it a go. And like I mentioned last time, I think the number one thing that sets our device now apart from the current device being used of just using calipers is the ability for our device to truly get into those inlet and outlet locations. A pair of calipers can only get just as far as the little like the little feet, I guess you could call them, on the calipers can actually get into the impeller, whereas our device can be inserted as far as you needed to in order to obtain the measurement, your desired measurement. In terms of using, like, being too complicated with having to tighten everything, how we designed it, the pair of snap ring pliers are always going open, so it always has the spring force pushing against the edges of the impeller. So whenever it hits those edges, we tighten it with one hand, and then you simply are just using the pliers with one hand and then the calipers with the other. So yeah, we feel that this process is still definitely more efficient and more accurate than what is currently being done now.
Yeah, and in terms of ergonomics, I think because of the way we designed it, like Jeremy said, with it having like naturally staying open, you only have to think about one thing at a time. So first you get it in there, and then it naturally stays open and in the position you want, and then you can focus on locking it. And then once it's locked, you can wiggle it around inside the impeller, but that measurement is still staying true. And then you just have to get the calipers on the feet of the tool, but calipers are easy to use with one hand. I mean, we found it really easy to use. And also the way that you hold it, again, it's hard to describe it without it in our hands right now. But the way you hold it, the wing nuts are out on, like, I guess, facing towards you, so that doesn't get in the way in terms of ergonomics. So we didn't find it to be an issue at all, but definitely having the locking mechanism was crucial to make it feasible and easy to use, because otherwise you would have to think too much about making sure the tool's in the right place. So that locking mechanism was really crucial in that area.
Okay, awesome. Yeah, that's good to hear. I have another question. You guys may have explicitly said it somewhere along during one of our weekly meetings, but maybe I just missed it. But I noticed that the design of the feet on the end that goes inside of the impeller is slightly different than the feet on the end that is measured by the calipers. I think I know the reason. I think it's pretty obvious, but I guess just to make sure I'm not assuming incorrectly, why was one end flat and one end looked like it was a half circle?
So that curvature was, I think this was on my slide. That curvature was so that our tool was only touching one point of the impeller at a time. Because if it was flat, you might get one corner of that flat foot touching and then the other corner. And this would create inconsistencies. And then the other side where you're using the calipers is flat because the flat measurement part, or sorry, the distance that it was extruded out is the same distance as the top of the arc of the feet on the top. So this way it's still the same measurement that you're getting, and you're able to put the calipers more easily on a flat surface than that arc that you would be trying to catch. That would just be too difficult. So we did think about that while we were designing it.
Okay, yeah, that's what I assumed. I just did wanted to verify that was the case, and it makes sense that the end that you're measuring is flat because obviously the pair of calipers, I mean, they have flat faces.
Yeah.
Okay, Awesome. So I guess after everything's said and done, again, this may be kind of similar to what I asked last time, but what was, in your guys' opinion, the most difficult or the most challenging part about this? If it was challenging, I don't know how. I mean, you kind of expressed some of the challenges along the way, but I don't know. All that's kind of relative.
Yeah, something that I had mentioned last time, and as being part of the really being in charge of the manufacturing of this device, was just the whole process of getting it CNC plasma cutted and getting it machined. I think was probably one of the most difficult for us, just because what we had available to us here at Penn State through the Learning Factory, and we were instructed and told by the Learning Factory staff after I used it that their equipment may not be calibrated quite properly. So that was definitely a hoop that we needed to try to jump through and work around. And all things considered, I definitely think that we took that, I guess you'd call it struggle head on, and were able to still come up with a solid, successful final project for you.
Sweet.
Are those all the questions you have?
I guess the last one, it's more of just kind of a yes or no, but the drawing that you had on screen was for an individually cut piece. Just curious, did you guys ever manage? I don't think I explicitly requested it, but did you guys seek out like like a drawing of the actual Irwin snap ring pliers themselves and use that to create, let's say, like an assembly drawing where you have both of the actual arms, the pin, the snap ring pliers, the bracket, the wing nuts, and everything?
I don't think we ever did manage to get to that. It kind of became a sprint towards the end with the manufacturing. But again, I guess that's something that with further considerations that maybe like flowserve is manufacturing everything, because it would make sense, because it would be kind of weird if you guys were bulk purchasing these snap ring pliers and then throwing away the heads to just throw on your own. But I don't like that specific snap ring plier doesn't have to be the one that's used. And it definitely would be probably easy enough to just make some sort of cross design with a spring attachment that has the pins in the right spot for the head attachment to go on. But we did not seek out that.
Okay, yeah, no problem. Go ahead.
I was going to say that, yeah, we have created SolidWorks models of the assembly of just the part that we actually developed working. And then also early on in the prototyping process, I did in SolidWorks, like from scratch, create a pair of pliers and put a head on them. But that obviously we went a different route from the beginning of this semester. So that model that I did create could be modified to fit what we're doing for this, but it wasn't specifically done, at least at this time.
Okay, yeah, no problem. And yeah, like I said, I didn't explicitly request it, so I didn't assume that to be like a for sure deliverable or anything. However, I would just recommend in the future, like anytime you make a component that's used, and whether it be a sub-assembly, part of a full assembly, always get like a full assembly drawing made. Whether
Okay.
like there's been projects I worked on in the past where I, let's say, have to make it'd be a sub-assembly used for, let's say, a pneumatic press. Let's say a bearing has to be press fit into the certain slot. I had to like reach out to the manufacturer of that hydraulic press and say, hey, this is the model we have. This is the model with whatever accessories. Can I have a drawing of this? And sometimes it's pretty easy. Sometimes you can just reach out to like a sales guy and they'll have the drawings immediately available, as long as it's not like a customized piece. Sometimes it can be difficult and you gotta like jump through a lot of hoops. But I just always recommend, if you do something like this in the future, always create not just a drawing for the individual piece or pieces you make, like this part or the sub-assembly, but like of the full assembly as well.
Okay. Yeah.
Yep, that's all I had.
Great.
But yeah, good presentation. I can't wait to. I don't think I given you my guy's address, or maybe the
No.
address of the office is. Yeah, but yeah, I can't wait to actually mess with it and and then see how easy it is. Oh, and then also the I guess the standard work instruction or the document alongside that. See that as well.
Yeah. Do you want us to print that out? And well, wait, Connor, you might be able to stop the recording now. But do you want us to print that out as if it was like a physical manual and put it in with what we're shipping back to you, or